Hello and welcome to this journey into the world of artificial intelligence, a story that explores how machines learn not just to assist humans, but to write code, solve complex problems, and ultimately begin coding the future themselves. In the next 10 parts, we will delve into the rise of OpenAI, a company that transformed the landscape of technology, research, and software development by harnessing the power of artificial intelligence. From the earliest experiments in machine learning to the groundbreaking achievements of generative models capable of producing human-like code, this is a story about curiosity, innovation, and the profound ways AI is shaping our world. We will begin by exploring the inception of OpenAI, its foundational principles, and the vision that guided its founders, a belief that artificial intelligence, if developed responsibly, could become a force for unprecedented progress. The early days were filled with experiments in natural language processing, reinforcement learning, and neural networks, as the team sought to understand how machines could learn, reason, and eventually perform tasks previously thought to require human intelligence. These experiments laid the groundwork for AI models that could comprehend language, generate text, and eventually write code, turning abstract concepts into actionable instructions for computers. As we move forward, we will uncover the challenges and breakthroughs that marked OpenAI's path. Early AI models were limited in capability, often producing results that were inconsistent or prone to error. Yet through iterative research, experimentation, and the integration of massive datasets, the organization developed architectures capable of learning patterns, understanding context, and applying logic in ways that mirrored human thought processes. These developments paved the way for AI systems that could read, interpret, and write code, bridging the gap between human creativity and machine efficiency. We will also examine the societal and technological implications of AI writing code. How does the ability of machines to program themselves change the software industry? What ethical considerations arise when AI becomes an autonomous creator? OpenAI's journey provides a lens through which we can explore these questions, highlighting both the incredible potential of AI and the responsibilities that accompany such transformative capabilities. The narrative will take you through the evolution of AI from a supportive tool to a creative partner in coding, illustrating the collaborative relationship between humans and machines that defines the modern technological landscape. The story will further detail the development of large-scale generative models, such as GPT, which became instrumental in enabling AI to write code. These models, trained on vast repositories of programming languages, documentation, and examples, could understand complex logic, produce functional code snippets, and even debug or optimize existing programs. We will explore how these capabilities revolutionize software development, accelerating productivity, reducing repetitive work, and opening new possibilities for innovation across industries. Throughout this journey, we will highlight key milestones: the development of codecs, the integration of AI into popular programming tools, and the collaboration between OpenAI and other technology leaders to ensure AI coding assistance is widely accessible. We will also explore how AI coding models are reshaping education, enabling learners to interact with programming concepts in a more intuitive and hands-on way. By studying these advancements, we gain insight into how AI is not only automating tasks but also enhancing human understanding and creativity in the field of computer science. Moreover, the story will discuss the broader impact of AI that can code itself. Beyond software development, these technologies are influencing scientific research, engineering, and even creative arts, as AI-driven tools allow professionals to prototype, simulate, and iterate faster than ever before. OpenAI's models have become catalysts for innovation, empowering humans to achieve more while redefining what it means to collaborate with machines. The narrative will explore both the opportunities and challenges, including ensuring reliability, ethical use, and maintaining human oversight in AI-generated code. By the end of this first part, you will understand not only the vision behind OpenAI but also the foundational principles that have guided its work in developing AI capable of writing code. This story is about exploration, creativity, and the transformative power of artificial intelligence. It is about a future where machines are not just tools but partners, capable of contributing meaningfully to the digital world we inhabit. As we continue, we will journey through the breakthroughs, the technology, and the real-world applications that demonstrate how AI has evolved from assisting humans to becoming an active participant in coding the future. So, buckle up and prepare to explore a world where artificial intelligence and human ingenuity converge, where lines of code are generated not only by human hands but also by the intelligent systems that OpenAI has developed. This is the story of how machines learn to write code, the evolution of AI programming, and the exciting possibilities that lie ahead as humans and machines collaborate in unprecedented ways. Welcome to the journey of OpenAI and the era of AI-driven coding. After the introduction of OpenAI, the journey toward AI that could write code began with a combination of ambition, experimentation, and a deep understanding of machine learning principles. The founders of OpenAI envisioned a future where artificial intelligence would not just assist humans in mundane tasks, but actively contribute to solving complex problems by generating its own code. Early experiments focused on natural language processing, teaching machines to understand context, syntax, and logical structures within human-written text. This foundation proved crucial, as the leap from language comprehension to code generation required machines to grasp not only grammar and semantics but also functional logic. The first attempts were modest. AI models could produce small snippets of code, often requiring significant correction and refinement by human programmers. Yet, these initial efforts were invaluable in demonstrating the feasibility of the concept. Researchers discovered that the same techniques used to predict the next word in a sentence could, with appropriate modifications, predict the next line of code. By training models on massive datasets of publicly available programming examples, AI systems began to learn the patterns, structures, and idioms of different programming languages, from Python to JavaScript, C++, and beyond. During this early stage, OpenAI faced numerous technical challenges. The AI often struggled with long-term dependencies, logical errors, and complex program structures. Solutions required not just more data, but improved architectures, attention mechanisms, and model scaling. Iterative experimentation led to the development of neural network architectures capable of handling longer sequences, understanding nested logic, and reasoning about functional dependencies within code. These models began to move beyond simple autocomplete functionality, reaching toward the capability to generate coherent, functional programs. One pivotal breakthrough came with the recognition that code, much like natural language, could be represented as a sequence of tokens. By converting code into tokenized forms, AI models could learn the probabilistic relationships between different programming constructs. This approach allowed AI to generate syntactically correct code more consistently and, increasingly, to suggest improvements, refactor existing code, and even identify potential bugs. The ability to reason about code structurally was a major step toward autonomous coding capabilities. OpenAI researchers also explored transfer learning, enabling models trained on one set of programming tasks to generalize across other domains. For instance, a model trained extensively on Python code could adapt its knowledge to write scripts in JavaScript or SQL. This versatility became a hallmark of AI-assisted coding, providing developers with a tool capable of handling multiple languages and frameworks without retraining from scratch. Transfer learning not only accelerated development, but also highlighted the potential for AI to become a universal coding assistant, adaptable to diverse technological environments. The release of the Codex model marked a watershed moment. Codex, trained on billions of lines of code, could interpret natural language prompts and generate functioning code in response. It represented a shift from experimental AI coding assistants to practical tools with real-world applicability. Developers could describe tasks in plain English, from creating a simple function to constructing complex algorithms, and Codex could produce executable code that solved the problem. This capability dramatically reduced the barrier to entry for programming and enabled professionals to focus on higher-level design and innovation rather than repetitive implementation details. Alongside technical innovation, OpenAI emphasized safety and reliability. Generating code autonomously comes with risks, logical errors, security vulnerabilities, and unintended behaviors could arise. OpenAI implemented safeguards, testing protocols, and feedback loops to ensure AI-generated code met acceptable standards. Human oversight remained essential, reinforcing the principle that AI is a collaborative tool rather than a replacement for human judgment. These practices established trust in AI coding assistants and demonstrated how machines could augment human capabilities responsibly. As codecs and related models matured, the implications became apparent. AI was no longer confined to experimentation, it had become a practical collaborator in software development. Enterprises integrated AI coding assistants into development pipelines, startups leveraged them to accelerate prototyping, and educators used them to teach programming concepts interactively. AI-generated code was improving productivity, accelerating innovation, and enabling more people to participate in creating software than ever before. By the end of this phase, the vision that had begun in OpenAI's laboratories had materialized. Artificial intelligence was now capable of understanding, reasoning about, and generating code. While early limitations remained, each iteration brought AI closer to a state where it could autonomously assist in building complex software systems. This development marked the beginning of a new era, where coding was not just a human skill but a collaborative process between humans and intelligent machines, setting the stage for the transformative impact that AI would have on the technology landscape. The story of AI learning to code illustrates a broader truth. Innovation often arises from combining disciplines in unexpected ways. By merging natural language understanding with programming logic, OpenAI unlocked the potential for machines to contribute creatively to software development. This achievement laid the foundation for future advancements, including autonomous problem-solving, intelligent debugging, and the creation of AI systems capable of learning and improving their own code over time. The journey had just begun, but the trajectory was clear. AI was becoming an indispensable partner in coding the future. As AI coding models like Codex matured, OpenAI faced the challenge of scaling their capabilities to meet the needs of real-world developers. Early experiments had demonstrated that AI could generate small code snippets, but practical software development required handling projects of much larger scope, multiple files, intricate logic, and integration with external systems. Scaling AI meant not only increasing model size but also improving context understanding, memory management, and the ability to reason over complex sequences of instructions. This was a pivotal moment, marking the transition from AI as a research experiment to AI as a practical partner in software engineering. To achieve this, OpenAI leveraged advances in model architecture, training strategies, and computational infrastructure. Large-scale transformer models were designed to handle long-range dependencies in code, ensuring that AI could maintain awareness of variable definitions, function calls, and interrelated logic across an entire project. Distributed training on high-performance GPUs allowed these models to process massive datasets, including open-source repositories, documentation, and real-world codebases, improving their understanding of idiomatic practices and common programming patterns. This combination of advanced architecture and vast data enabled AI to generate code that was not only correct but also efficient and maintainable. Integration into developer tools became the next step. OpenAI partnered with platforms like Visual Studio Code, GitHub, and other IDEs, embedding AI-powered assistants directly into the coding environment. Developers could now receive suggestions, auto-completions, and even entire function implementations in real time as they typed. This integration transformed the coding experience. Repetitive tasks were automated, boilerplate code was generated instantly, and developers could focus on high-level design, logic, and creative problem-solving. AI became a seamless collaborator rather than an external tool, working alongside human programmers in the environments they already used. One of the most significant breakthroughs was enabling AI to interpret natural language prompts and translate them into functional code. By describing a desired functionality in plain English, developers could have AI generate code that implemented their specifications. This capability democratized programming, lowering the barrier to entry for beginners while enhancing the productivity of experienced engineers. Students, hobbyists, and professional developers alike could leverage AI to prototype ideas quickly, test concepts, and iterate faster than ever before. It was a radical shift in how software could be created and experienced. The scaling of AI also introduced autonomous debugging and optimization capabilities. AI models could analyze code for errors, suggest fixes, and even propose performance improvements. By learning from patterns in millions of existing code examples, AI could detect subtle logical errors, security vulnerabilities, and inefficient constructs that might elude human eyes. This ability not only improved code quality but also accelerated development cycles, as developers could rely on AI to catch mistakes and optimize solutions before deployment. AI became both a creative and a quality assurance partner. OpenAI recognized that ethical and responsible deployment was critical. AI-generated code, if misused, could introduce security risks or propagate biases present in the training data. To mitigate these issues, safeguards were implemented, including prompt filtering, model fine-tuning, and human oversight. OpenAI emphasized that AI was a tool to augment human capability, not replace it, ensuring that developers retained control and responsibility for the code they deployed. This approach built trust and allowed organizations to confidently adopt AI-assisted coding in critical systems. As adoption grew, so did the range of applications. Enterprises used AI to accelerate software delivery pipelines, automate testing, and generate custom solutions for clients. Startups leveraged AI to prototype and scale products rapidly, often with smaller engineering teams than traditional development would require. Educational institutions incorporated AI assistants to teach programming, allowing students to experiment, learn from instant feedback, and explore creative solutions without getting bogged down in syntax or repetitive code. Across industries, AI was reshaping the landscape of software development. Moreover, OpenAI explored collaborative coding workflows, where multiple AI models and human developers could work in parallel on complex projects. AI could generate foundational code, while humans refined, integrated, and optimized it. This synergy allowed for faster innovation and higher quality software, demonstrating the potential for AI-human partnerships to enhance productivity and creativity. It became clear that AI coding assistants were not merely tools but collaborators, capable of contributing meaningfully to software engineering projects of any scale. By the end of this phase, AI had evolved from an experimental coder of small snippets to a robust partner capable of assisting in real-world software development. Its ability to understand context, reason about logic, and interact with human developers transformed the nature of programming itself. OpenAI's vision was coming to life: machines that could understand human intentions, generate code, and collaborate intelligently. This period marked the beginning of a new era where AI was no longer a background tool but an active participant in creating the software that powers modern life. The journey of scaling AI and integrating it into practical development demonstrated a profound shift in the relationship between humans and machines. Developers were no longer isolated problem solvers. They were part of a collaborative ecosystem where AI amplified their capabilities, handled routine tasks, and enabled rapid experimentation. This evolution laid the groundwork for even more advanced AI coding systems, capable of autonomously generating complex architectures, learning from feedback, and continuously improving over time. OpenAI had not only taught machines to write code, it had begun teaching them to innovate alongside humans. As AI coding models grew in complexity and scale, OpenAI realized that raw computational power alone was insufficient. To truly create AI that could write code effectively, the models needed to learn from human feedback, refining their outputs based on guidance, corrections, and preferences from experienced developers. This phase marked a turning point. AI would no longer simply predict code patterns from data. It would begin to reason, adapt, and improve iteratively based on interaction with humans. The concept of reinforcement learning from human feedback, RLHF, became central to this evolution. By allowing AI models to generate multiple coding solutions and then receive evaluations from human experts, the models could adjust their internal parameters to favor higher quality, more functional outputs. This approach mirrored the way humans learn: trial, error, and correction. Through RLHF, AI began to understand not only syntax and logic but also best practices, coding style, and functional intent, creating code that was more reliable, readable, and maintainable. Fine-tuning through human feedback also allowed AI to understand context at a deeper level. Previously, AI could handle individual functions or small modules, but complex projects required awareness of interdependencies, long-term logic, and subtle design decisions. Developers could guide AI to follow architectural patterns, respect code conventions, and consider security implications. The models learned to weigh trade-offs, optimize performance, and anticipate potential errors. AI coding assistants were no longer just generators of text. They were collaborators capable of thoughtful reasoning about the software they helped create. This phase also emphasized adaptability. By continuously incorporating feedback from diverse coding styles, programming languages, and application domains, AI models became versatile tools. Whether generating web applications, data analysis scripts, or embedded systems code, the AI could adjust its approach to match the context. Fine-tuning enabled models to handle not only common tasks but also specialized requirements, giving developers a partner that could tackle a wide array of programming challenges efficiently. OpenAI also explored interactive development environments, where AI could respond in real time to suggestions, corrections, and queries. Developers could ask why a piece of code was generated a certain way, request alternative implementations, or guide the AI to optimize specific components. This two-way dialogue transformed programming into a collaborative conversation, bridging human intuition with machine computation. The AI was learning not in isolation but in tandem with human reasoning, enhancing its ability to generate meaningful, context-aware code. An important aspect of this stage was error recognition and correction. AI models learned to identify their own mistakes, whether logical inconsistencies, security vulnerabilities, or inefficiencies. By analyzing failed executions or feedback from developers, the AI could propose corrections autonomously. Over time, this self-reflective capability allowed models to produce more reliable code with fewer iterations, reducing the cognitive load on human collaborators and improving overall productivity. Beyond technical improvements, RLHF introduced ethical and safety considerations into AI coding. OpenAI ensured that AI-generated code adhered to security best practices and avoided harmful or unsafe patterns. Developers could provide explicit feedback on undesirable outputs, helping the model learn to avoid generating code that could be exploited or cause unintended consequences. This focus on responsible AI development reinforced the principle that AI should augment human capability safely, not act as an uncontrolled agent. The impact on education and skill development was significant. Students and junior developers could receive immediate guidance on coding techniques, style, and problem-solving approaches. AI acted as a tutor, offering explanations, suggesting alternatives, and highlighting potential pitfalls. This feedback-driven learning accelerated human skill acquisition while also improving the AI's own performance through continuous exposure to diverse problem-solving strategies. The relationship between human and machine became symbiotic. As humans taught, AI learned. As AI improved, humans benefited from smarter assistants. Industry adoption flourished as AI coding assistants, now fine-tuned through RLHF, proved capable of handling complex projects with minimal supervision. Enterprises integrated AI into development workflows for rapid prototyping, testing, and deployment. Startups used AI to scale software creation with lean teams. Across sectors, AI accelerated time to market, improved code quality, and reduced human error, demonstrating the transformative potential of AI-human collaboration in programming. By the end of this phase, AI models were no longer static tools. They were adaptive, context-aware collaborators, capable of reasoning, learning from feedback, and producing code that reflected human intent and best practices. OpenAI had unlocked a new dimension of AI coding capability. Machines that could not only write code but continuously learn, improve, and align their outputs with human guidance. This stage set the foundation for even more advanced developments, where AI could understand complex project requirements, optimize systems holistically, and participate in creative problem-solving alongside human developers. The evolution of AI through human feedback demonstrated a fundamental principle. Intelligence, whether artificial or human, thrives on iteration, correction, and guidance. By incorporating this principle into AI coding models, OpenAI had created systems capable of meaningful collaboration, capable of understanding context, reasoning logically, and contributing creatively to the development of software. The journey toward machines that could autonomously code while aligning with human intent had entered a new and transformative chapter. As AI coding models became more sophisticated and fine-tuned through human feedback, they began to tackle larger, more complex projects. The early days of generating individual functions or small scripts had evolved into a new era. AI could now assist in designing entire software systems, understanding interdependencies, architectural patterns, and project-level logic. This transition marked a fundamental shift in how developers approach software creation, as machines became collaborators capable of contributing to complex problem-solving workflows. The key to this evolution was contextual understanding. Advanced AI models could maintain awareness across multiple files, modules, and even projects spanning several repositories. They understood how different components interacted, how data flowed through systems, and how functional requirements influenced design choices. By keeping track of these relationships, AI could suggest coherent solutions that aligned with both technical and functional objectives, enabling developers to work more efficiently while maintaining the integrity of large-scale software. Collaboration between AI and human developers became increasingly sophisticated. AI could generate initial implementations, propose alternative algorithms, and refactor code for readability, performance, and maintainability. Developers could review these outputs, provide feedback, and guide the AI toward preferred approaches. This iterative process created a dynamic feedback loop, where both human and machine contributed to problem solving. Over time, AI models became more proactive, anticipating design patterns, suggesting optimizations, and even detecting potential errors before they were executed. One notable application was in enterprise software development, where projects often required adherence to strict standards, integration with legacy systems, and coordination among multiple teams. AI coding assistants helped streamline workflows by generating standardized code, automating repetitive tasks, and ensuring consistency across modules. This capability reduced development time, minimized human error, and freed engineers to focus on high-level strategy and innovation rather than routine implementation details. Organizations experienced faster product cycles and improved reliability, illustrating the tangible benefits of AI-assisted software creation. In parallel, AI began contributing to creative and experimental software projects. Startups and independent developers leveraged AI to prototype ideas quickly, explore alternative solutions, and iterate on design concepts without the need for large teams. By generating code for complex systems such as web applications, mobile apps, and embedded solutions, AI enabled developers to test ideas in real time, accelerating innovation and allowing for rapid experimentation. The collaborative dynamic between humans and AI transformed coding into a creative partnership, where machines could contribute insights and solutions that complemented human intuition. The AI's capacity to handle cross-disciplinary knowledge was another critical advancement. Models could integrate knowledge from multiple domains, such as mathematics, data science, and engineering, to generate software that solved specialized problems. For example, AI could assist in building simulations, automating data analysis pipelines, or generating code for scientific research. By bridging knowledge domains and translating abstract concepts into functional software, AI extended human capability, allowing developers to focus on conceptual design and problem-solving rather than implementation minutiae. Security and reliability continued to be focal points. As AI took on more responsibility in complex projects, ensuring that generated code adhered to best practices, avoided vulnerabilities, and followed ethical guidelines was paramount. OpenAI implemented robust verification tools, continuous testing protocols, and feedback mechanisms to guarantee that AI-generated solutions were safe, dependable, and maintainable. This approach reinforced trust in AI as a responsible collaborator, capable of contributing to mission-critical projects without compromising quality or security. In educational settings, AI's role expanded to include guidance on system-level thinking. Students could experiment with multi-module projects, receiving advice on architecture, design patterns, and integration strategies. The AI provided explanations, alternative solutions, and recommendations, accelerating the learning process and fostering deeper understanding of complex software engineering principles. This educational impact reinforced AI's potential as both a tool and a teacher, capable of enhancing human learning while improving its own problem-solving capabilities through feedback and iterative interaction. By this stage, AI coding assistants were no longer merely helpers. They were collaborators that could manage significant portions of large projects. They could generate core components, maintain consistency across modules, optimize performance, and provide ongoing suggestions throughout the software lifecycle. Developers began to view AI as a partner, capable of accelerating innovation, improving quality, and enabling creative exploration in ways that were previously unimaginable. The implications for the software industry were profound. AI-assisted development reduced bottlenecks, shortened development cycles, and enabled teams to tackle projects that would have previously required far more resources and expertise. Startups could compete with larger companies, individual developers could produce sophisticated applications, and enterprises could accelerate innovation without proportionally increasing headcount. AI had become a force multiplier, enhancing human capability and redefining the limits of software development. By the end of this phase, it was clear that AI had progressed from generating isolated code snippets to participating in the creation of complete software systems. Through contextual understanding, collaborative feedback, and multi-domain knowledge integration, AI coding assistants had become indispensable partners in development workflows. OpenAI's vision of machines that could code autonomously while working alongside humans was now a tangible reality. The era of AI as an active collaborator in software creation had arrived, setting the stage for even more ambitious applications, where AI would not only generate code but also reason about design, optimize systems, and participate in the full lifecycle of software engineering. As AI coding assistants matured and began handling complex projects, OpenAI turned its focus toward generative programming, a domain where AI could not only follow instructions but also create entirely new algorithms and approaches to problem solving. This phase represented a leap from code generation as a service to AI as a creative collaborator, capable of inventing novel solutions to challenges across technology, science, and engineering. The ability of AI to innovate in programming marked a transformative stage in the evolution of machine intelligence. Generative programming relies on AI's ability to analyze patterns, extrapolate concepts, and combine knowledge across domains. By training on vast datasets encompassing multiple programming languages, mathematical algorithms, and engineering principles, AI models could generate solutions that were not simply reproductions of existing code but original implementations informed by learned patterns. This capability allowed developers to approach problems with a partner that could suggest unconventional solutions, optimize performance in ways humans might overlook, and experiment with alternative methods at unprecedented speed. One of the most striking impacts of generative programming was in the creation of novel algorithms. AI could design sorting, searching, and optimization routines tailored to specific datasets and constraints. In areas like data science, AI suggested unique approaches for analysis, pre-processing, and feature selection. In simulations and modeling, AI could construct algorithms to accelerate computations, handle large-scale data efficiently, and optimize resource usage. By doing so, AI became not just a coding assistant but a collaborator in innovation, contributing original ideas to problem-solving workflows. Generative AI also facilitated rapid prototyping. Developers could describe a problem or desired functionality in plain language, and the AI could generate multiple alternative implementations, each with varying trade-offs in speed, memory usage, and complexity. By comparing these options, human developers could select, refine, and optimize the most suitable solution. This iterative cycle dramatically accelerated the development process and enabled experimentation that would have been too time-consuming using traditional coding methods. Another critical application of generative programming was in emerging technologies, including artificial intelligence itself. AI models could write supporting code for machine learning frameworks, generate scripts for data preprocessing, or even create components of other AI systems. This recursive innovation, AI assisting in the development of AI, amplified productivity and facilitated rapid advancement in the field. Researchers could focus on conceptual innovation while AI handled implementation details, accelerating progress in areas such as neural network design, reinforcement learning experiments, and model optimization. Collaboration between human ingenuity and AI creativity became a defining feature of this era. Developers provided guidance, constraints, and objectives, while AI explored possibilities, generated prototypes, and suggested improvements. The human-AI partnership created a synergistic workflow, where AI extended human capacity for problem-solving and experimentation. Complex challenges, from optimizing distributed systems to designing new algorithms for computational biology, could now be tackled more efficiently and effectively. OpenAI also emphasized the importance of safety and evaluation in generative programming. AI-generated algorithms, while innovative, required rigorous testing to ensure correctness, efficiency, and security. Feedback mechanisms were integral, allowing humans to validate outputs, highlight potential issues, and guide AI toward more reliable and practical solutions. This ensured that creativity did not compromise quality, maintaining trust in AI as a collaborator capable of producing not just functional but robust code. Generative programming also transformed educational approaches. Students could explore advanced concepts by interacting with AI-generated algorithms, learning alternative methods for solving problems, and receiving explanations about complex structures and optimizations. AI became a mentor and collaborator, revealing multiple pathways to solutions, exposing learners to creative approaches, and accelerating comprehension of abstract concepts. This enriched both human learning and AI refinement, as feedback from educational use contributed to iterative improvements in model performance. The industry implications were profound. AI-assisted generative programming enabled rapid experimentation, optimized workflows, and accelerated innovation across domains. Startups leveraged AI to prototype cutting-edge applications quickly, enterprises integrated AI to streamline research and development, and academic institutions adopted AI tools to advance computational exploration. By contributing original algorithms and creative solutions, AI became a force multiplier for human innovation, extending what was possible in both research and industry. By the end of this phase, it was evident that AI had moved beyond coding by instruction to coding by creativity. Generative programming demonstrated that AI could participate in problem-solving at a conceptual level, propose novel solutions, and accelerate innovation in ways that complemented human intelligence. OpenAI had successfully created AI systems capable of reasoning, innovating, and collaborating in the creation of software and algorithms, marking a significant milestone in the journey toward autonomous, intelligent coding systems. The era of AI-driven generative programming revealed a fundamental truth: collaboration between humans and intelligent machines could expand the boundaries of what was possible in technology, science, and engineering. By combining human insight with AI creativity, OpenAI had enabled a new paradigm in software development, one in which machines were not only assistants but co-creators, innovators, and partners in coding the future. As AI coding capabilities advanced, their impact extended far beyond traditional software development. OpenAI's models, having evolved from code autocompletion to generative programming, began transforming industries, demonstrating that AI could contribute meaningfully to enterprise operations, healthcare innovation, and creative pursuits. The ability to generate code, design algorithms, and propose solutions in specialized domains meant that AI was no longer confined to programming. It was becoming a versatile collaborator across diverse fields. In the enterprise sector, AI coding assistants revolutionized software development workflows. Large organizations faced the challenges of maintaining complex systems, integrating legacy software, and accelerating digital transformation. AI could generate modules that adhered to enterprise standards, automate repetitive processes, and optimize system performance. It also facilitated collaboration across teams by ensuring consistency, proposing scalable architectural patterns, and even analyzing the potential impact of design decisions. Companies reported increased productivity, faster deployment cycles, and reduced technical debt, all while maintaining high-quality standards. Healthcare was another area experiencing profound change. AI-assisted programming enabled the rapid development of tools for medical research, data analysis, and patient care applications. Models could generate scripts to analyze genomic data, optimize medical imaging algorithms, and assist in building predictive models for disease diagnosis. AI helped bridge the gap between research and implementation, allowing scientists and engineers to quickly translate complex medical insights into functional software applications. This capability not only accelerated innovation but also improved patient outcomes by enabling faster, data-driven decision-making. Creative industries also benefited from AI coding capabilities. Game developers, animators, and digital artists leverage AI to prototype interactive experiences, generate scripts, and create complex simulations. AI-assisted programming allowed creators to focus on the conceptual and artistic aspects of their projects, while AI handled technical implementation, debugging, and optimization. This collaboration accelerated the production process, reduced barriers to entry for emerging creators, and expanded the potential for innovation in digital media, virtual reality, and interactive storytelling. The cross-industry adoption of AI coding also encouraged multidisciplinary problem-solving. In engineering, AI helped design control systems, optimize logistics, and simulate complex processes. In finance, AI generated algorithms for predictive modeling, risk assessment, and automated reporting. Even in scientific research, AI assisted in coding simulations for physics experiments, climate modeling, and computational chemistry. By adapting to different knowledge domains, AI became a flexible, domain-aware collaborator capable of contributing to tasks that required both technical expertise and creative thinking. OpenAI emphasized that industry adoption required responsible and transparent use. AI-generated code needed to meet ethical and security standards, especially in sensitive sectors like healthcare and finance. By implementing feedback loops, review mechanisms, and human oversight, OpenAI ensured that AI acted as a trustworthy collaborator, capable of augmenting human efforts without introducing risk or unintended consequences. This approach helped organizations integrate AI with confidence, unlocking its potential while maintaining accountability. Education and workforce development were also impacted. Professionals could leverage AI to learn new programming paradigms, experiment with complex systems, and explore innovative solutions in their fields. AI served as a mentor and collaborator, accelerating skill development and enhancing human creativity. In healthcare, engineers could prototype algorithms for patient monitoring systems. In enterprise, teams could simulate optimization strategies. In creative industries, artists could test interactive designs. The AI-human collaboration became a catalyst for professional growth and interdisciplinary learning. One of the most compelling outcomes was AI's ability to accelerate innovation cycles. Startups and enterprises could iterate on software and systems faster than ever before. Prototypes could be generated, tested, and refined in record time, while AI provided insights and suggestions that were often novel or counterintuitive. This rapid experimentation enabled organizations to explore ambitious projects without excessive resource investment, democratizing innovation and expanding the frontiers of what was technologically possible. The era of AI across industries highlighted a profound truth: artificial intelligence was no longer merely a tool for coding. It was a strategic collaborator, capable of driving efficiency, creativity, and innovation across sectors. By understanding human intent, generating functional solutions, and learning from feedback, AI contributed to enterprise decision-making, healthcare advancements, and creative expression. OpenAI's vision of machines as collaborative partners had manifested on a global scale, reshaping the way industries approached problem-solving, design, and implementation. By the end of this phase, it was clear that AI had moved beyond isolated coding tasks to becoming an integral part of industrial and creative ecosystems. Enterprises leverage AI to optimize operations, healthcare professionals used it to accelerate research and improve outcomes, and creators employed it to unlock new realms of artistic and interactive expression. The transformative potential of AI coding assistants demonstrated that collaboration between humans and intelligent machines could extend across every sector, unlocking unprecedented opportunities for innovation, efficiency, and creativity. OpenAI had successfully created AI systems that were not only capable of coding but capable of understanding context, adapting to specialized domains, and collaborating meaningfully with humans. The stage was now set for even broader applications, where AI would continue to evolve, learning from complex environments, anticipating needs, and contributing proactively to the advancement of human knowledge and capability. As AI coding assistants became deeply integrated across industries, their role began to reshape entire software ecosystems. Beyond generating code or optimizing specific functions, AI models now contributed to automating complex workflows, orchestrating large-scale systems, and supporting collaborative innovation. OpenAI's vision of AI as an active participant in technological development was now unfolding on an unprecedented scale, influencing not just individual projects but the architecture of software ecosystems themselves. One of the most impactful changes was the emergence of AI-assisted software orchestration. Large-scale systems often involve multiple interconnected components, services, and platforms, requiring coordination and consistent design practices. AI models could now analyze dependencies across systems, propose integration strategies, and even automate deployment pipelines. By understanding relationships between components, AI helped maintain consistency, optimize resource allocation, and prevent errors that could arise from misalignment between modules. Developers found that AI could manage complex project topologies, reducing manual oversight while ensuring robustness and scalability. The introduction of AI-driven workflow automation further accelerated productivity. Routine tasks, such as code refactoring, testing, documentation, and deployment, were increasingly handled by AI, freeing developers to focus on strategic design, innovation, and problem-solving. AI could monitor code repositories, detect inefficiencies, and proactively suggest improvements across entire projects. In effect, AI became a project-level collaborator, capable of coordinating efforts, maintaining standards, and ensuring quality across distributed teams. This capability transformed the software development lifecycle, turning it into a continuous, intelligent, and adaptive process. Another major contribution was in innovation management. AI models could simulate various design alternatives, predict performance outcomes, and evaluate trade-offs across multiple solutions. Developers could explore a broader range of possibilities without the prohibitive time investment typically required for manual experimentation. This accelerated the pace of discovery, allowing teams to innovate faster, optimize more effectively, and deliver cutting-edge solutions. In industries ranging from finance to healthcare to gaming, AI-enabled experimentation became a competitive advantage, providing insights and strategies that were previously out of reach. The scale of AI involvement also extended to collaborative coding environments, where multiple human developers and AI systems worked simultaneously. AI could suggest improvements in real time, reconcile conflicting approaches, and maintain coherence across the codebase. This collaborative ecosystem enabled distributed innovation, allowing teams spread across geographies to contribute efficiently while AI mediated and enhanced the workflow. The result was faster iteration cycles, higher quality outputs, and a stronger alignment between conceptual goals and implemented solutions. In addition, AI's integration into software ecosystems introduced advanced monitoring and optimization capabilities. AI could analyze system performance, detect bottlenecks, and recommend architectural changes or code adjustments. In cloud-based environments, AI-assisted optimization helped reduce costs, improve latency, and ensure scalability. By participating in both the design and operational phases of software, AI became a full lifecycle contributor, bridging the gap between development and deployment, and ensuring systems remained robust and adaptive over time. OpenAI also focused on maintaining ethical, secure, and reliable AI practices at this scale. Automated code generation and system management required safeguards against vulnerabilities, logic errors, and unintended consequences. Continuous feedback loops, human oversight, and rigorous validation protocols ensured that AI contributions met safety standards and aligned with organizational goals. This balance of autonomy and oversight reinforced trust, enabling enterprises to confidently adopt AI as a strategic collaborator in innovation pipelines. Education and research were similarly transformed. Students, researchers, and engineers could experiment with complex software systems, receive guidance from AI, and iterate rapidly on innovative designs. AI acted as both mentor and assistant, exposing users to advanced techniques, proposing optimizations, and suggesting alternatives that expanded creative and technical horizons. This symbiotic relationship between human intelligence and machine reasoning accelerated knowledge transfer, skill development, and the exploration of novel solutions in ways previously unimaginable. By the end of this phase, AI had evolved into a core component of software ecosystems, participating in design, development, deployment, and optimization at scale. Its role extended far beyond coding to include orchestration, workflow management, collaborative problem-solving, and strategic innovation. Organizations leveraging AI experienced unprecedented efficiency, creativity, and adaptability, highlighting the transformative potential of human-AI partnerships in shaping the future of technology. The era of AI-driven ecosystems demonstrated a crucial principle: intelligence is most powerful when it collaborates. By integrating context awareness, predictive reasoning, and creative problem-solving, OpenAI had created systems capable of supporting large-scale innovation while augmenting human capability. AI was no longer just a tool, it had become an indispensable partner in designing, building, and optimizing the complex software landscapes that define the modern world. As AI coding systems continued to mature, OpenAI turned its attention toward mastering collaboration and self-improvement, envisioning a future where AI could not only assist humans but also autonomously refine its own capabilities. This phase represented the culmination of years of iterative development, human feedback, and domain adaptation, highlighting AI's potential to become a proactive participant in software innovation, capable of learning, optimizing, and contributing independently while remaining aligned with human goals. Central to this evolution was the development of self-improving AI models. Through continuous learning pipelines, AI could analyze the outcomes of its own code, evaluate performance, detect errors, and adjust internal parameters to enhance future outputs. This iterative refinement enabled models to evolve beyond the limitations of initial training datasets, incorporating lessons from both successes and failures. As a result, AI became increasingly adept at generating efficient, robust, and innovative solutions across a wide range of applications, from enterprise software to scientific simulations. Collaboration between humans and AI reached a new level of sophistication. AI could now anticipate developers' needs, offer proactive suggestions, and propose multiple strategies for achieving project goals. This predictive capability reduced cognitive load on humans, enabling them to focus on creative and strategic aspects of software design. Teams could work seamlessly with AI as an intelligent partner that understood context, reasoning, and objectives, fostering an environment where human ingenuity and machine intelligence complemented each other in unprecedented ways. Autonomous innovation became particularly notable in complex, large-scale projects. AI systems could generate modular architectures, optimize interdependencies, and even propose entirely new frameworks for solving technical challenges. Developers could guide AI with high-level goals and constraints, while the AI explored solution spaces that humans might not have envisioned. This combination of guidance and exploration accelerated discovery, allowing projects to evolve rapidly, adapt to changing requirements, and maintain high standards of quality and performance. One of the most remarkable developments was AI's ability to learn from its interactions across diverse domains. By participating in projects spanning software development, data analysis, engineering, and creative industries, AI models accumulated a wealth of knowledge and experience. This cross-domain learning enabled AI to transfer insights from one context to another, suggesting innovative approaches and algorithms that leveraged interdisciplinary principles. The result was a system capable of holistic problem solving, bridging gaps between fields and accelerating innovation in ways that were previously unimaginable. Self-improving AI also enhanced reliability and robustness. By continuously analyzing generated code, monitoring outcomes, and incorporating human feedback, AI could detect and correct errors proactively. Security vulnerabilities, logic inconsistencies, and performance bottlenecks were identified and mitigated autonomously, reducing the likelihood of failure and improving trust in AI-assisted software development. This capability ensured that as AI contributed more autonomously, it remained aligned with both functional requirements and ethical standards. The impact on research and education was profound. AI-assisted laboratories, coding platforms, and simulation environments enabled students and professionals to experiment with complex systems, explore alternative strategies, and learn from AI-driven insights. The feedback loop was mutual. Human input refined AI's performance, while AI accelerated human learning and problem-solving. This symbiotic relationship fostered innovation, deepened understanding, and prepared the next generation of engineers and developers to thrive in an AI-enhanced landscape. In industry, self-improving AI transformed product development cycles. Organizations could prototype, test, and deploy software faster than ever before. AI-assisted experimentation reduced trial and error, optimized resource allocation, and enabled more ambitious projects. Enterprises reported shorter time to market, higher quality software, and improved adaptability in dynamic markets. Startups leveraged AI to compete with larger players, democratizing access to sophisticated development tools and expertise. Across sectors, AI became a force multiplier, extending human capability and accelerating innovation. By this stage, AI coding assistants had evolved into autonomous collaborators capable of learning, adapting, and contributing independently while remaining integrated with human workflows. The models could understand context, anticipate challenges, and propose innovative solutions, all while maintaining alignment with project objectives and ethical guidelines. OpenAI had demonstrated that AI could move beyond reactive assistance to proactive participation, fundamentally transforming the nature of software development. The journey toward mastering collaboration and self-improvement underscored a profound truth: intelligence flourishes in interactive, iterative, and adaptive environments. By combining human insight with AI's computational power, reasoning, and creativity, OpenAI had created systems capable of autonomous innovation while remaining guided by human intent. This phase set the stage for the final chapter of the story, where the full potential of AI in coding, collaboration, and innovation would be realized, heralding a new era of human-AI partnership in shaping the future of technology. As we reach the conclusion of this journey through the evolution of AI in coding, it becomes clear that what began as a tool for auto-completion has transformed into a profoundly intelligent collaborator, capable of creativity, reasoning, and autonomous innovation. OpenAI's vision of AI not merely as an assistant but as a partner in software development has materialized, demonstrating that machines can amplify human ingenuity while contributing original ideas and solutions. From early models predicting code snippets to self-improving systems capable of designing entire software architectures, AI has redefined the landscape of programming. It has accelerated development cycles, reduced human error, and expanded the boundaries of what is technically feasible. Generative programming and reinforcement learning from human feedback have enabled AI to understand context, adapt to diverse domains, and propose novel solutions that enhance both creativity and efficiency. The transformative impact of AI coding extends across industries and disciplines. Enterprises leverage AI to streamline operations and maintain complex software ecosystems. Healthcare professionals use AI-generated algorithms to accelerate research and improve patient outcomes. Creative industries employ AI to design immersive experiences and interactive media. In education, AI serves as a mentor, guiding students and professionals through complex concepts while providing feedback that accelerates learning and skill acquisition. Across every domain, AI has become a force multiplier, extending human potential and fostering innovation at unprecedented speed. A crucial aspect of this evolution is collaboration. AI is not a replacement for human developers but a partner that enhances human capability. By integrating human feedback, anticipating needs, and continuously refining its own outputs, AI engages in a dialogue with developers, contributing to problem solving in ways that are thoughtful, context-aware, and often unexpected. This partnership has demonstrated that the greatest potential of AI lies not in independence but in cooperation with human intelligence, producing outcomes neither could achieve alone. The journey of AI in coding also emphasizes the importance of responsible development. OpenAI's approach to ethics, safety, and transparency ensures that AI systems produce secure, reliable, and socially responsible outputs. By embedding safeguards, testing protocols, and feedback mechanisms, AI's growing autonomy is balanced with accountability. This principle ensures that as AI assumes greater roles in software creation and innovation, it continues to align with human values and societal goals. Looking to the future, the implications are profound. AI's ability to self-improve, generate original algorithms, and participate in complex, large-scale projects hints at a new era where software development is co-created by humans and intelligent machines. The speed of innovation, quality of software, and creative potential unlocked by this partnership are unparalleled. We can envision AI assisting in the design of entire technological ecosystems, contributing to scientific discovery, and supporting creative endeavors that push the boundaries of human imagination. Moreover, AI is poised to transform how humans approach learning and problem-solving. By providing real-time guidance, alternative strategies, and adaptive feedback, AI empowers individuals to think more critically, experiment more boldly, and create more ambitiously. It democratizes access to sophisticated tools, enabling individuals and small teams to achieve outcomes that previously required extensive resources or expertise. This accessibility fosters equity in innovation and accelerates the pace at which new ideas can be explored and implemented. Ultimately, the story of AI coding is one of human-machine partnership. It is a narrative of machines learning from humans, humans learning from machines, and both evolving together to achieve outcomes neither could accomplish alone. OpenAI's work illustrates that intelligence, whether human or artificial, thrives in collaboration, iteration, and feedback. By embracing this principle, AI has transitioned from a tool into a partner capable of shaping the future of technology, society, and creative endeavor. As we close this chapter, it is evident that the AI-powered era of coding is not just about efficiency or automation. It is about expanding human potential. AI augments our ability to innovate, explore, and solve problems at scales and speeds previously unimaginable. It challenges us to rethink the boundaries between human creativity and machine intelligence, inviting us to envision a future where collaboration with AI is a central component of progress. In conclusion, the evolution of AI in coding represents a new dawn for technology. From the first predictive models to self-improving, autonomous collaborators, AI has demonstrated its ability to revolutionize how software is created, optimized, and applied across domains. It is a testament to what can be achieved when human ingenuity meets machine intelligence. A future where the partnership between humans and AI unlocks possibilities limited only by imagination, driving us toward a world of unprecedented innovation and discovery.